So question one, listen, these two questions are going to appear exactly like this on the test. Honestly, I don't even know if it's word for word, but I don't feel any shame in just telling you straight up. You need to know both of these. You already know them both. You just may not know in the context that, oh, this is what you're talking about. The general standard form of a quadratic function or a quadratic equation is this one. Y equals ax squared plus bx plus c. You've used this so many times in my presence where with the quadratic formula and finding the vertex negative b over 2a. So, I mean, that's something that's right familiar. Just know that that's standard form. And we call it the general form because it's got input slots for a, b, and c. So like a, b, and c are obviously going to be numbers at some point, but it's just waiting. And anytime you have something that's just waiting for numerical input, it's just a sort of a general form of an equation or a formula. Okay. Anyone remember vertex form, the second one?
The y just equals a plus b in parentheses squared plus c.
That was a really good effort, honestly. And I know I'm sarcastic a lot, but it's not right, but you dug that up out of the archives. So this one has come up in class before. If you were to remember what it was, I would be massively impressed, by the way. Um, it's y equals a times x minus h squared plus k. You could dig back through the archive of your notebook and you could go back several weeks, maybe a month, 5 weeks, and you'd actually find the day that we talked about that. And part of the push in our class, in this class, was I wanted you guys to get really good at converting standard form quadratics into vertex form quadratics. And we love vertex form because the vertex just falls right out. And there's like hardly any work to do, right? So if I said to graph one that's in vertex form, it's almost like a joke, but we'll get to practice that here in a bit. So top one is general form of a standard quadratic. Second one is general form of a vertex quadratic. They are equivalent. They just are in different formats. Any questions about one or two? You're allowed to use a page of notes on the district assessment whenever it is. So make sure that you prepare one. I cannot allow you to open your notebook to that one page. Like you can't say, can I just use this page? It has to be a physical separate entity that you create and that you forfeit. Okay. So make sure it's an actual standalone page. And to not put something like that on there would be sinful. I mean, for God's sake, how long would it take you to write that in your notes? Like 15 seconds? Totally worth it. I don't really feel like I need to go over number three with you. That should be pretty fresh in your memory from recent stuff where we pull out the four, complete the square, blah, blah, blah. If you don't remember how to do that, I'll refresh your memory when the time comes, okay? Question four is sort of a use your words kind of thing. So what we're interested in on question four is, can this student describe to us the changes that are going to take place? So like you guys all know that the parent function, again, going way back in time, is this. So the question becomes, what changes does the graph of y equals x squared undergo based on that equation on the board? So like, what's one of the changes you might say? It goes up 5. What else?
Left 3.
It goes left 3. What else?
Slope of -4.
It has a slope of 4, which means that, our normal, what are our normal parabola values? Like if I say out 1, we go up 1, out 2, up 4, out 3, up 9. Those are the normals, right? We double them, or in this case, quadruple them because there's a 4, right? You remember that? And then also because it's a negative, what's another transformation that happens? What's a negative make us do? Go downwards, right? So no longer is it going out and up, it's going out and down, and it's going to be pretty skinny. So the section number 4 is a place for you just to use your words and describe those transformations that the graph undergoes. Everything you do to change a parent function is called a transformation.
Is there like a set like right answer, or is it?
Yes, I mean, the right answer to this one is you dang well better describe all four transformations.
Okay. Well,
Flipping upside down, getting skinny by a factor of 4, moving left 3, moving up 5. Every one of those just has to be addressed. If the negative wasn't on the 4, then you'd only have to have 3 parts to your answer. Because if there's no negative, then it doesn't get flipped upside down, right? So your job in that problem is just to describe using words what happens to the graph. Question 5 is the last one I'm really going to be up in your business about, just because I did not write this particular district assessment. When the tasks were divvied up, I was more in charge of writing the Algebra 1 tests in a team than I was the Algebra 2 tests. So I love this test. This part of it is more specific to the person that was more in charge over in Pine who wrote the test. So I need to go over a couple things with you so that you know what these questions are asking. These are not vocabularies or terminologies that I use in my class. And I just want you to, in fairness, to know what they are. So let's look at that equation in problem 5, first of all. Tell me about it, like right now. Where's it going to go?
to the right.
It's going to go right 3. What else? Down 7. There's going to be the vertex. It's going to open up or down?
Up.
Skinny or fat?
Fat.
Fat. So remember, that's how we approach graphing in my class. Mr. Walter over in Pine, he approaches it a little bit differently. So as I go through this problem with you, it might make more sense kind of how he has his students do the graphing. We're going to all wind up generally with the same thing at the end of the day. So first, let's talk about amplitude. The word amplitude generally should not even be used in conjunction with a parabola like this. It's normally, if you ever go on and take any course that involves trigonometry, you'll graph. Have you guys ever heard of like sine and cosine waves? Like sound waves, you know? And you know what happens like on a radio dial or like something, if you turn the knob to a higher, yes, you see that those waves, whoom, they shoot up and they have more what we call amplitude, right? Whereas if you shrink them, then the amplitude of a curve is generally the distance from the middle of it up to its highest or down to its lowest point, which is why the term really shouldn't be applied to this. But it is here and it's on the test. And to be a team player, let's just hammer this out. Where do you think I could get the amplitude of this graph?
From like the
From the
top
one
of the
third.
graph.
And that's the problem with this, is that there is no top of the graph, and there is no, like with graphs that open upwards, there's never going to be a top, right? And so that's why this term is really not very normal here. But the amplitude is generally going to be described by this, the 1/3. So we would say that the amplitude is 1/3. And then you'll notice it kind of says to describe it. So let's use our words and describe. Like, what does that mean to us? As students who learned how to graph parabolas in this classroom, what does it mean to us?
It's gonna be fat.
Okay, that's a word you could use. Is it's going to open fatter, right? But let's do a little bit more specifics on that. Let's hit it a little bit closer. What did we learn about the number 1/3? How's it going to mess with our graph?
Let's go slash it out.
Yeah, you could say like all of the y changes, I guess, are 1/3 as much. I mean, I know a lot of you are just going to take my words and transcribe them, and I'm okay with that, but you can use your own words too. What we're trying to get across here is can we collectively show the powers that be that we understand that the number 1/3 has this effect or impact on the graph? And that's what on this test you're expected to know as amplitude. Got it? Any questions about that? Okay. And I'll wind up giving you probably more practices just because I'm kind of going over these with you. I always kind of feel bad when I do that. The y-intercept. So this is where you really get a good look. These next 3 problems are where you get a really good look at how Mr. Walter over in Pine Bluffs teaches his students to graph parabolas. We have completely different approaches to this process. So here comes his. First thing he does is he has his students find the y-intercept. And as you know, what that means is the y-intercept is the place where the graph crosses the y-axis, right? I'm going to put a bunch of red dots. And then I'm going to erase them. And, you know, other than the typical sarcastic responses like they're all red or they're all circles or something stupid. And obviously they're all on the y-axis. So if we discount that they're all red, that they're all circles, and they're all on the y-axis, what do all the red points have in common?
X.
Say it again.
An X of 0.
That is perfect. What every one of those points has in common, first off, we agree every one of those is called a y-intercept, right? I mean, that is the definition of a y-intercept, a point on the y-axis. They all, Andrew said it, have x coordinates of 0. You could point to any one of them and say, well, it's 0, 4, 0, 6, 0, -2, 0, -4.5. They all have that consistently, that x is 0, right? Yeah, that's worth flexing on. That's a good observation. And the thing about it is, and this can apply to any level of mathematics. If someone comes at me and says, hey, I need you to find a y-intercept, all I'm going to do is change x into 0. It's not like finding a y-intercept in algebra 1 where all we had to do was like look at the end. You guys remember y equals mx plus b?
Yeah.
Like if I gave you y equals 4x minus 7, what's the y-intercept? Down 7, -7, right? That was easy, but it doesn't work that way. Like you can't look at this and say, oh, the y-intercept is -7 just because of that. It doesn't work that way with quadratics. So what we're going to do is we're going to take 0 and we're going to put it in place of x, and that's going to enable us to find the y-intercept. So here it goes. Up here in this equation, we're going to change x into 0, right where this little arrow is pointing right there. Boop. So it's going to say 1/3 of 0 minus 3 squared minus 7. What's 0 minus 3?
-3.
What's -3 squared?
9.
What's 1/3 of 9?
3.
And what's 3 minus 7?
-4.
So we can say that the y-intercept is at 0, -4. If I went too fast, just come talk to me later and I'll go through it with you again super slower. But just to reiterate, what I wrote in this fatter pen is the key. Just anytime you want a y-intercept, change x into 0, work it out. Okay. So that means that the y-intercept is down here at 0, -4. Right there. I'm going to graph it. You should too. There. Now we also know how to find the vertex. If the problem was written in standard form, ax squared plus bx plus c, we would do our cute little -b/2a formula. But because it's written in vertex form, what a joke, right? What's the vertex of this function?
3.
+3, -7. So the vertex is at +3, -7. Now, this brings me then, and I don't think there's really anything to describe here. I mean, I can't describe the vertex. I mean, it's the bottom of the, I'm not going to hold it against you if you don't describe it. Find it. That leads me to this cryptic guy. The world is a symmetric point. You could Google this and you won't get any results. And again, this is because this was written sort of from the perspective of someone who uses certain words in their classroom. And since we're just going to take the district test, I'll just tell you what he means. He means this. You see you got a vertex, right? And then you see you got this point right here. And you know, having done parabolas with me before, that there's going to be another point over here someplace, right?
Yeah.
That's called a symmetric point. Again, you won't find that on the internet because it's sort of a niche word that he uses in his class. But his logic is, well, if you already know the y-intercept is up here and you know the vertex is down here, then there has to be another point, 1, 2, 3, 1, 2, 3, right here as well. So this point is what he would expect us to call the symmetric point. Were we going to find that anyways?
Yeah.
Yes, which is why I don't worry about it, but we would have found it using our own method. So our method for graphing is going to be a little bit more precise because we are going to take the 1/3 that's in the front and we're going to modify all of our normals. Ready? So here it goes. If we go out 1, how far up do we go?
1/3.
Normally 1, we go 1/3 of 1, which is 1/3, just like that. Remember this? We go out 2. Normally, we'd go up 4. What's 4 divided, or 1/3 of 4?
1.25.
1 and 1/3. Like that. We already know these, but let's just verify them so we feel good about this. If we go out 3, normally we'd go up 9. But what's 1/3 of 9? And that's what these two red points already are. I'm not happy if you guys graph the vertex and the y-intercept and the symmetric point. That to me is not a good enough graph. I've expressed how I feel about this before. I'm going to graph as many points as this particular piece of graph paper will allow me to graph. So because you're stuck with me, you get to graph more with me also. So when we go out 4, how far up would we normally go?
6.
16, but what's a third of 16?
5 and a third.
5 and a third. So I'm going to go up 1, 2, 3, 4, 5 and 1/3, which is right about here. Big old bossy Mr. Ahern's like, do I have to do more? Of course I have to do more. Until I run out of real estate, I'm going strong. If I go out 5, how far up would I normally go? But what's a third of 25?
8 and a third.
8 and a third. And I think we got room for one more. If we go out 6, we'd normally go up 36. What's a third of 36? 12. So I got enough room to go out 1, 2, 3, 4, 5, 6. 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm pretty sure if we try to go again, that we'll be cutting it pretty close. You might be able to squeeze one more in up there, but that's pretty dang good right there. So anyways, you can kind of see the differences in how different people teaching the same thing come at it from two very different approaches. But uh, again, since I didn't really have a hand in writing this test, then I would ask that you play along and use the lingo. The amplitude, remember, is really just our A value. It's like the descriptor of how fat or skinny the graph is effectively. And then the y-intercept, recap. How do you find a y-intercept?
Make x equals 0.
Make x equals 0. And then what's the symmetric point?
Or opposite side.
It's just the point on the other side from the y-intercept, right? And of course, if the y-intercept is 0, or if the vertex is at the y-intercept, then there's no symmetric point really per se. So get the idea. Do you have any questions on anything I've discussed so far? Okay. You will encounter some things as you go that you just need a refresher on. Please just let me be involved in that process. I don't care today if you work on assignment 50 or if you work on this. I would leave it to you as long as you choose one of those two. Okay. And if you do want to talk about assignment 50, the problem that I wrote on, then I will talk to you about that as well. Whatever you'd like. Sound good? Okay.
Wait, imaginary number.